PreAP, PreCalculus, Notes 3.4. The title says zeros of polynomial functions, but specifically, we're going to focus on what multiplicities of zeros means, what it implies about the graph. We're going to also discuss in this section what the end behavior of the graph is. So let's do end behavior first. For each of the functions graphed below, state the end behavior and the zeros of the function. Let's focus on end behavior. End behavior means as we travel to the left forever, what's happening to the graph? As we travel to the right forever, what's happening to the graph? Now, you don't really have a lot of choices of what's going to happen. In polynomial functions, what's going to happen as you go left forever, it's going to go up or down. As you go right forever, it's going to go up or down. The notation for this is the most complicated part. Looking at this cubic function that we see here, what's the left end behavior? So let me first write down the question. The question symbolically is what is the limit of the function f of x as x approaches negative infinity? Reading this without symbols, this is asking what's happening to y as x goes left forever? Now, if you look at this, as x goes left forever, y is going down. Since y is going down forever, we would say the answer to this question is it's going to negative infinity. The right end behavior is asking what's happening to function f as x goes to infinity. Reading it with limits, the limit of f of x as x approaches infinity is equal to, if you follow this graph, as we go right forever, the graph is going up forever. Symbolically, y going up forever is positive infinity. Without knowing the answer to these questions, these answers start out the same way every time. The left end behavior is asking what's happening to the function as x approaches negative infinity. And the right end behavior, what's happening to the function as x approaches positive infinity. Looking at this next graph, we'll get the zeros here in a minute. Looking at the next graph, as x goes left forever, y is going up forever. So as x approaches negative infinity, the limit is infinity. As x approaches positive infinity, y is going up forever. It's also approaching positive infinity. This is a quartic function. Quartic meaning that the biggest exponent for this is a 4. A quintic function means the biggest exponent, the degree is 5. So for this particular quintic function, as you go left forever, the function goes down. That means y is approaching negative infinity. As you go right forever, y is going up. That means that y is approaching positive infinity. We'll also find the zeros of these functions. For this cubic function, f of x, we have a 0 of -2, -1, and 1. For g of x, just going to estimate that it's -2.5 and possibly 2. It's really hard to tell there. For h of x, looks like -4, -2, 2, and 5. So let's now get into this multiplicity question. So that was end behavior. Let's talk about multiplicity. Defining multiplicity. The multiplicity of a 0 0 is an x-intercept. In this case, we'll say it's x equals a, is the number of times x minus a is a factor of the function. If you recall in the previous section, the factor theorem says that if x minus a is a factor, then x equals a is a zero. So this is saying that any x-intercept, its multiplicity, is the number of times that x minus that x-intercept is a factor of the function. Now there are lots of things that can be implied from this that we are going to get into here coming up soon. Read the following information about the multiplicities of zeros of f, g, and h while studying the graphs above, and answer the questions on the next page. So on function f, all the zeros have a multiplicity of 1. So let's look at this. So even though we don't know what the actual equation is, it's saying this multiplicity is 1, this one's 1, and this one's 1. We know that because it tells us. It just tells us right here. On g of x, the 0 of x equals negative 2.5 has a multiplicity of 1, and x equals 2 has a multiplicity of 3. Interesting. I'm just going to point out here 1, 1, 1. We're told this one was 1 and this multiplicity was 3. On h of x, the zeros of negative 4, negative 2, and 5 have a multiplicity of 1. X equals 2 has a multiplicity of 2. So this one was 2. This multiplicity is 1, 1, and 1. Just to be clear, if these multiplicities are 1, for example, for this x minus 4, this x-intercept of negative 4, it means that x plus 4 would be a factor 1 time. If negative 2 is a 0 and its multiplicity is 1, it means x plus 2 is a factor 1 time. If 2 is a 0 and its multiplicity is 2, x minus 2 is a factor 2 times. And then finally, if 5 is a 0 and its multiplicity is 1, x minus 5 is a root 1 time. What does that mean? It means that we have the power now to write the actual function for the graph of h, knowing where the x-intercepts are and what the multiplicity is of each of these. It's pretty powerful and it's pretty cool, I think. 1, what do you notice about the sum of the multiplicities of the zeros in the degree of the function? Now, this isn't always true, what we're going to write down, because there could be imaginary roots. So let's assume right now that we're talking about functions that only have real roots. If we're only talking about real roots, the degree will equal the sum of the multiplicities. So like, for example, multiplicity of 1 plus 1 plus 1 is 3, it's cubic. Multiplicity of 1 plus 3 is 4, it's quartic. Multiplicity of 1 plus 1 plus 2 plus 1, that's not right. 1 plus 1 plus 1 plus 2 is 4, plus 1 is 5, quintic, 5. Describe the behavior of the graph as it approaches zeros whose multiplicity is 1. If the multiplicity is 1, looks like the graph is crossing the x-axis. Now the same thing's happening at 3, but something different's happening at 3, and we'll get into that in a second. Describe the behavior of a graph as it approaches a zero whose multiplicity is 1. The graph will cross the x-axis without changing concavity. Let's discuss what concavity is. This graph I just drew is concave down. This graph is concave up. If I take a graph that's concave down and I take a graph that's concave up and I put them together like this point here is a point where the concavity is changing. At that point, it's either concave up nor concave down, but the concavity is changing there. So I'm suggesting that if the multiplicity is 1, it crosses the x-axis and the concavity does not change. Describe the behavior of a graph as it approaches, let's do this one. Describe the behavior of the graph as it approaches 0 whose multiplicity is 3. Well, it's the same thing we said here, but the concavity does change. The graph will cross the x-axis and changes concavity. Now this multiplicity of 3, we're just talking about these graphs. This is 3. What we're really saying is that it's odd and at least 3. So it could be 5, 7, 9, 11. Same thing's going to happen. The concavity is going to change and it's going to cross the x-axis. The only example we have on our picture here is this one right here. This right here is concave down, and this part here is concave up. It is changing concavity at that point. Describe the behavior of the graph as it approaches 0 whose multiplicity is 2. Now it's just not restricted to 2, it's really any even multiplicity. If it's an even multiplicity, the graph is tangent to the x-axis. It touches it and goes back the direction in which it came. So we're going to say the graph is tangent to x-axis and we'll also say, we'll say and doesn't change concavity. It's only changing concavity if it's an odd degree of 3 or more. If it's 1 or 2, it doesn't change concavity. If it's 1, well, if it's any odd number, it's going to cross the x-axis. If it's an even multiplicity, it will be tangent to the x-axis. This is really, really powerful stuff. So these problems here, we're just going to basically drive home what we already know, just to show you how this works. For each of the following functions, you're given a factor of the function. So like for f, we are given a factor of x plus 1. Identify the 0 associated with the factor. It's one thing we're supposed to do. Then use synthetic division. It's 2 things we have to do to determine how many times the given factor is a factor of the function. Then identify the multiplicity of the root with that factor. There are 3 things that we're supposed to do. 1, according to the factor theorem, since this is a factor, we're going to have a root of -1. It's whatever number I can put into this factor for x to make this equal to 0, and that's -1. So that's done. Now we're supposed to use synthetic division. So I'm going to take the coefficients of 1, 2, -1, and -2, and I'm going to divide it by the root of -1, dividing it by the factor of x plus 1 synthetically. If I throw 0 in here, if I add down, I get 1. -1 times 1 is -1. If I add down, I get 1. If I multiply, I get -1. If I add, I get -2. If I multiply, I get +2. Now I'm not surprised. This ends up being a root at least once. I'm not surprised because I was told it was a factor and the picture shows that that's happening. Now let's try this again, because the direction says use synthetic division to determine how many times it's a factor. So I'm going to do this again. Every time you do synthetic division for a depressed polynomial, it just keeps coming a less term each time. So 1 plus 0 is 1. -1 times 1 is -1. I add. and I multiply, and I get a remainder of -2. This is not a factor more than once. Determine how many times the given factor is a factor. X plus 1 is a factor once. Then identify the multiplicity of the root. Well, if it's a factor once, the multiplicity is 1. Now, we knew this going into it, because we were told that, but we're just showing you, hey, this actually works. And then identify the multiplicity of the root associated with the factor. We did that. And here it says, describe the behavior of the graph at this root. The graph crosses the x-axis at x equals -1 without changing concavity. Each time you're either going to be saying if it's crossing or tangent, then you're going to say if it is or is not changing concavity. Next one, we've got function h, and we are focusing on the factor of x minus 1. The factor theorem tells us that a root of this has to be x equals 1, because 1 is the number you would put into this to make this equal to 0. We're now going to divide this synthetically. We're dividing it by 1. So I add and I multiply, and I add and I multiply, and I add and I multiply. Remainder 0. Not surprised. Will this happen again? Well, let's see. Add, hold on, let me put this one a little higher, put it in a box. And I multiply, and I add, and I multiply. Hey, it happened twice. Let's see if it happens 3 times. Add, and I multiply, and I get a remainder of 5. So it worked 2 times. So I would want to say x minus 1 is a factor twice. The multiplicity, therefore, is 2. Describing the behavior of the graph at this root, the graph is tangent to the x-axis. At x equals 1 without changing concavity. Not 100% sure if we even need to say this, because if it's tangent, it's not going to change concavity. I mean, it's possible theoretically, but not with anything that we're doing. Let's look at one more of these, and then we'll cut this video off, and then we'll finish this up in another one. We've got function p of x. We got a factor of x minus 1. The factor theorem would tell us that 1 has to be a root. If I put a 1 into this, 1 minus 1 is 0. I'm going to use synthetic division, because the directions told me to see how many times 1 is a factor. The graph clearly shows it's a factor once. So I add and I multiply, and I add and I multiply, and I add and I multiply, and I add and I multiply. So it works once for sure. Let's try her again. Add and multiply, add and multiply, add and multiply. Well, it works 2 times for sure. See if we can get it to work a 3rd time. Add and multiply, add and multiply. Hey, it works 3 times. See if we can get it to work a 4th time. Add and multiply. Did not work the 3rd time, which is fine. So to answer the question, x minus 1 is a factor thrice, 3 times. Multiplicity then is 3. Describe the behavior of the graph at this root. The graph crosses the x-axis. You know what? I want to go back and fix something here. I wasn't specific when I said the graph. We need to name the graph each time. That is a really important thing. The graph f of x. The graph h of x. If I just say the graph, the reader may not know which graph we're referring to. And then here, it's the graph p of x. Crosses the x-axis at x equals 1 and changes concavity. I know for sure that if we have an odd multiplicity, we want to say if it changes concavity or not. For the even ones, we could probably get away without saying it because the graphs we have, the even ones, will never change concavity. All right, that concludes the first part of the notes. And what we basically discussed was what is end behavior. And we have this notation that we can do end behavior with. And we also discussed multiplicity of zeros, what that means, and how it affects the graph.